Hello all. Today we are discussing about strategies and payoff. So as we already mentioned at the end of section 3, that is in a matrix game, if the payoff matrix that is Aij has a saddle point Rs, then I equal to R and J equal to S are the optimal strategies of the game, and the payoff ARS is called the value of the game. Suppose assume that if the matrix has no saddle point, then the game has no optimal strategies in the above sense. So by introducing probability with choice and mathematical expectation with payoff, the concept of optimal strategy can be extended to apply to all matrices. So this we proceed to do. Let P1 choose a particular I such that I equal to 1, 2, 3, etc. m with probability xi. We may also interpret it as a relative frequency with which P1 chooses I in a large number of plays of the game. The probabilities xi, I equal to 1, 2, 3, etc. m constitute the strategy of P1. Similarly, if P2 chooses a particular j with probability yj, the probabilities yj such that j equal to 1, 2, 3, etc. n are the strategy of P2. So here we are bringing expectation. That is like P1. That is P1 is our first player and P2 is our second player. And strategies of P1 are 1 to m. That is, we are taking strategies of P1 as 1 to m and strategies of P2 are 1 to n. And for each strategy, or we can say, or for each move, we are assuming a probability. Next is a definition, mixed strategy. So let us look what is a mixed strategy. The vector x equal to set xi of non-negative numbers xi, that is, here xi's are non-negative numbers. നമ്മൾ xi എന്ന് പറയുന്നത് P1ൻ്റെ I ചൂസ് ചെയ്യുന്നതിൻ്റെ പ്രോബബിലിറ്റി ആയിട്ടാണ് നമ്മൾ എടുത്തിട്ടുള്ളത്. സോ ഹിയർ all xi's are non-negative numbers such that summation I equal to 1 to n xi equal to 1 is defined as mixed strategy of P1. That is, vector x is the mixed strategy of P1 such that all xi's are non-negative numbers. Also, summation I equal to 1 to m xi equal to 1, and vector x will be an element of em. Similarly, the vector y equal to set yj of non-negative numbers yj such that summation j equal to 1 to n yj equal to 1 defines the mixed strategy of P2. That means in a mixed strategy, the player will select more than one strategy. We define Sm as a set of ordered m tuples of non-negative numbers whose sum is unity. That is, Sm is a set of ordered m tuples of non-negative numbers whose sum is unity, and say that x belongs to Sm. Similarly, y belongs to Sn. Next definition, pure strategy. The mixed strategy x equal to theta I whose ith component is unity and all other components are equal to 0 is called a pure strategy of P1. That is, pure strategy means it is a mixed strategy whose ith component is unity and all other components are equal to 0 is called a pure strategy of P1. Similarly, y equal to eta j where all the components of y except jth are 0 is called a pure strategy of P2. Next definition, mathematical expectation. The mathematical expectation or the payoff function E of xy in the game whose payoff matrix is A equal to Aij is defined as E xy equal to sigma over I equal to 1 to n sigma j equal to 1 to n xi aij yj, which is equal to x transpose ay. That is mathematical expectation, or the payoff function e of xy in the game whose payoff matrix is A, which is equal to aij, is defined as like this. That is e of xy expectation, mathematical expectation, equal to sigma over I equal to 1 to m sigma j equal to 1 to n xi aij yj, which is equal to x transpose ay. And x and y are the mixed strategies of P1 and P2. So P1 should choose x for what? To maximize his least expectation. Okay, P1 should choose x for so as to maximize his least expectation, and P2 should choose y so as to minimize his greatest expectation. Okay, that is P1 should choose x to maximize his least expectation, um, and P2 should choose y so as to minimize his minimize P1's greatest expectation. That is P1 aims at maximum over x, minimum over y, e of xy, and P2 aims at minimum over y, maximum over x, e of xy. Next definition. If maximum over x, minimum over y, e of xy equal to minimum over y, maximum over x, e of xy equal to e of x naught y naught, then x naught y naught is defined as the strategic saddle point of the game. Okay, so if maximum over x, minimum over y, e of xy is equal to minimum over y, maximum over x, e of xy, which is equal to e of x naught y naught. In such a situation, we can say that x naught y naught is a strategic saddle point of the game, and x naught and y naught are defined as the optimal strategies, and v equal to e of x naught y naught is the value of the game. Okay, that is v equal to e of x naught y naught will be the value of the game. And then, by fundamental theorem of the theory of rectangular games, we can say that a strategic saddle point always exists. Now let us consider an example. Consider the matrix game. So this is our game. Here two players P1 and P2. Then IJ, first strategy, second strategy. Okay. Now we can say that in the matrix given, it has no saddle point, because if we find maximum over I, minimum over j, aij, its value is 3. How we will get it? If we take the row minimum, in the first row minimum value is 1 and second row minimum value is 3. So in that we take the maximum value, that is 3. Okay, so maximum over I, minimum over j, aij will be equal to 3. And if we find minimum over j, maximum over I, aij, it will be 4. That is we take the column maximum. In the first column maximum value is 5 and the second column maximum value is 4. So comparing that two values, minimum value we will take the minimum value, that is 4. So minimum over j, maximum over I, aij equal to 4, but 3 is not equal to 4. So the above matrix is without a saddle point. Now let the mixed strategies of P1 and P2 be x equal to closed interval x1 x2 and y equal to closed interval y1 y2. Okay, that is we take x as the mixed strategies of P1 and y is a mixed strategy of P2. Okay, and here x1 it means probability of player 1 choosing first strategy, and x2 is probability of player 1 choosing second strategy. Now we will find expectation, that is e of xy. We know the equation. E of xy equal to summation I equal to 1 to m summation j equal to 1 to n xi aij yj. Okay, so by substituting the values we get E of xy equal to 5 x1 y1 plus 3 x2 y1 plus x1 y2 plus 4 x2 y2. Also, in this equation x1 plus x2 equal to 1 and y1 plus y2 is equal to 1. It is we have seen in the definition. Okay, so next we are eliminating x2 and y2. That is, in the place of x2 and y2 we can substitute x2 equal to 1 minus x1 and y2 equal to 1 minus y1. So in the above equation, that is 5x1 y1 plus 3x2 y1 plus x1 y2 plus 4x2 y2, in the place of x2 we will write 1 minus x1 and in the place of y2 1 minus y1. Okay, so after that we get E of xy equal to 5x1 y1 minus 3x1 minus y1 plus 4. Okay, so this is after the cancellation we will get this equation. Okay, now we are factorizing this equation. Okay, so we will get like this: 5 x1 minus 1 by 5 y1 minus 3 by 5 plus 17 by 5. Okay, that is after factorizing the equation we will get this. Okay, now we can choose a strategy. That is, if P1 player 1 chooses x1 equal to 1 by 5, then the first term will become 0. Okay, then he ensures that his expectation is at least 17 by 5. Also, he cannot be sure of more than 17 by 5 because by choosing y1 equal to 3 by 5, P2 can keep E of xy down to 17 by 5. Okay, that is P1, the aim of P1 is to minimize the loss, but P2 aims at maximizing the loss of P1. Okay, so P1 might as well settle for 17 by 5 and play x naught equal to 1 by 5 and 4 by 5. Okay, that is if we choose x1 as 1 by 5, then x2 will be 1 minus x1, that is 1 minus 1 by 5, which is equal to 4 by 5. So we get x naught equal to closed interval 1 by 5 and 4 by 5, and that time P2 reconcile to minus 17 by 5 and play y naught equal to closed interval 3 by 5, 2 by 5. That is, if we choose y1 equal to 3 by 5, then y2 will be 1 minus y1, that is 1 minus 3 by 5, which is equal to 2 by 5. Okay, so these are the optimal strategies for P1 and P2. And E of xy, that is expected value, will be the value of the game. That is, the value of the game is 17 by 5 and x naught y naught is a saddle point of E of xy. Theorems of matrix games. So first theorem, let A be an m by n matrix and Pj and Qi, where j equal to 1 to n, I equal to 1 to m, be its column and row vectors respectively. Okay, so it is given that A is an m by n matrix and Pj and Qi, j varies from 1 to n and I varies from 1 to m, are its column and row vectors. Then either, first condition, there exists a y in Sn such that Qiy less than or equal to 0 for all I, or there exists an x in Sm such that x transpose Pj greater than 0 for all j. Okay, so the theorem states that A is an m by n matrix and Pj and Qi are its column and row vectors, then either there will be a y in Sn such that Qiy less than or equal to 0 for all I, or there exists an x in Sm such that x transpose Pj greater than 0 for all j. Now we can look the proof. So let zeta I belongs to Sm be a vector such that its ith component is unity and all other components are 0. Okay, let zeta belongs to Sm is a vector such that its ith component is unity and all other components are 0. Now consider the m plus n points, that is zeta 1, zeta 2, etc. zeta m, and p1, p2, etc. pn, which are belonging to em. And let C be the convex hull of the m plus n points. Then the origin 0 of em is either in C or not in C. Okay, so that we will get two cases. So case 1, let the origin be in C. Then the origin can be expressed as a convex linear combination of the m plus n points, which will span C. Okay, hence we can say that there exists lambda 1, lambda 2, lambda 3, etc. lambda m, mu1, mu2, mu3, etc. mu n belongs to Sm plus n. Okay, that is condition number 1, such that summation I equal to 1 to m lambda I zeta I plus summation j equal to 1 to n mu j pj equal to 0, where summation I equal to 1 to m lambda I plus summation j equal to 1 to n mu j equal to 1, and that is equation number 2. Okay, now equating ith component of each side, we get lambda I plus summation j equal to 1 to n mu j aij equal to 0, where I varies from 1 to m. Okay, that is equation number 3. Therefore we can say that summation j equal to 1 to n mu j aij equal to 0, I equal to 1 to m. Why? Because since lambda I is greater than or equal to 0, and that is equation number 4. Also summation j equal to 1 to n mu j greater than 0. For if summation j equal to 1 to n mu j equal to 0 implies mu j equal to 0 for all j, because mu j greater than 0. So equation 3 implies that lambda I equal to 0 for all I, but it is a contradiction to condition 2. Now what we will do is that we will divide 4 by summation j equal to 1 to n mu j. So we will get summation j equal to 1 to n mu j aij by summation j equal to 1 to n mu j, which is greater than or equal to 0 for I equal to 1 to m. Now we put yj equal to mu j by summation j equal to 1 to n mu j. Okay, then we get summation j equal to 1 to n mu j aij is less than or equal to 0 for I equal to 1 to m. That is Qiy less than or equal to 0 for I equal to 1 to m. Then y equal to y1, y2, y3, etc. yn transpose, clearly y belongs to Sn, since summation j equal to 1 to n yj equal to summation j equal to 1 to n mu j by summation j equal to 1 to n mu j, which is equal to 1. Now let us consider case 2. Suppose origin doesn't belong to C. Then there exists a hyperplane with equation Bz equal to 0 passing through C, such that C is contained in the open half space. default set such that b z greater than 0. Now b zeta I greater than 0 for I equal to 1 to m. Why? Because since zeta I belongs to C, which implies bi greater than 0 for I equal to 1 to etc. m. Therefore, we get summation I equal to 1 to m bi is greater than 0. Also, b pj greater than 0 for j equal to 1 to n since pj belongs to C. So we get summation I equal to 1 to m bi aij is greater than 0 for j equal to 1 to n. Okay. Now dividing by summation I equal to 1 to m bi, we get summation I equal to 1 to m bi aij by summation I equal to 1 to m bi is greater than 0. Now we put xi equal to bi by summation I equal to 1 to m bi, where I equal to 1 to etc. That is, in the place of xi we put bi by summation I equal to 1 to m bi, which implies summation I equal to 1 to m xi aij is greater than 0 for j equal to 1 to n. That is, x transpose pj is greater than 0 for j equal to 1, 2, 3, etc. n. So clearly x belongs to Sm, since summation I equal to 1 to m xi equal to summation I equal to 1 to m bi by summation I equal to 1 to m bi, which is equal to 1, and xi equal to bi by summation I equal to 1 to m bi, which is greater than 0 for I equal to 1 to etc. m. Next theorem, for an m by n matrix game, both maximum over x minimum over y e of xy and minimum over y maximum over x e of xy exist and are equal. That is, the theorem states that for an m by n matrix game, both maximum over x minimum over y e of xy and minimum over y maximum over x e of xy will exist and it will be equal. Now let us look at the proof. For each fixed y belongs to Sn, E of xy equal to x transpose into A into y, and it is a continuous function of x over a closed bounded set Sm of Em. Since therefore maximum over x E of xy exists. Okay, and it is a continuous function of y over Sn of En. Since Sn is closed and bounded, minimum over y maximum over x E of xy exists. Similarly, maximum over x minimum over y E of xy exists. Now by theorem 1, that is the first theorem by the previous theorem, that is if A is an m by n matrix and Pj and Qi are its column and row vectors respectively, then we studied that either there exists a y in Sn such that Qiy less than or equal to 0, or there exists x in Sn such that x transpose Pj greater than 0. Okay, so by that theorem, we have either Qiy less than or equal to 0, where I equal to 1 to m, that is equation number 1, or we have x transpose Pj greater than 0, where j equal to 1 to n, that is equation number 2. So first let us assume that first condition holds, that is Qiy is less than or equal to 0. That is summation j equal to 1 to n aij yj less than or equal to 0 for I equal to 1 to m and for some y belongs to Sn. Now what we will do is that we multiply both sides by xi and adding over I equal to 1 to m, we get summation I equal to 1 to m summation j equal to 1 to n xi aij yj less than or equal to 0. That is, E of xy less than or equal to 0 for all x equal to matrix A x1 x2 x3 etc. xm transpose. And also this is true for all x belongs to Sm. So we have maximum over x e of xy less than or equal to 0, and minimum over y maximum over x e of xy less than or equal to 0. If now suppose assume that if equation number 2 holds, then by similar argument we can say that maximum over x minimum over y e of xy is greater than or equal to 0. So if either one first condition or second condition holds, then maximum over x minimum over y e of xy is less than or equal to 0, less than minimum over y maximum over x e of xy is false. Okay. Now let AK denote the matrix obtained by subtracting k from each element of A. That is, AK is a matrix which is obtained by subtracting k from each element of K. That is, AK equal to Aij minus k. If suppose that Ek of xy denotes x transpose into Ak into y, then Ek of xy equal to x transpose into Ak into y, which is equal to summation I equal to 1 to m summation j equal to 1 to n xi aij minus k yj, which is equal to summation I equal to 1 to m summation j equal to 1 to n xi aij yj minus summation I equal to 1 to m summation j equal to 1 to n xi k yj, which is equal to summation I equal to 1 to m summation j equal to 1 to n xi aij yj minus k into summation I equal to 1 to m summation j equal to 1 to n xi yj, which is equal to E of xy minus k. Now since A is an arbitrary matrix, we get that what is false for A is also false for AK. Okay, that is, A is an m by n matrix, so what is false for A is also false for AK. Hence maximum over x minimum over y ek of xy less than or equal to 0, less than minimum over y maximum over x ek of xy is false, which implies maximum over x minimum over y e of xy minus k less than or equal to 0, less than or equal to minimum over y maximum over x ek of xy minus k is false, which implies maximum over x minimum over y e of xy less than or equal to k less than minimum over y maximum over x e of xy is false. Okay, k is arbitrary. This means that minimum over y maximum over x e of xy equal to maximum over x minimum over y e of xy. But by theorem 1 that we studied earlier, that is, the theorem states that f of xy be such that both maximum over x minimum over y f of xy and minimum over y maximum over x f of xy exists, then maximum over x minimum over y f of xy is less than or equal to minimum over y maximum over x f of xy. So by that theorem, we have maximum over x minimum over y e of xy is less than or equal to minimum over y maximum over x e of xy. Hence, minimum over x maximum over x minimum over y e of xy equal to minimum over y maximum over x e of xy, which is equal to e of x naught y naught. Next theorem, e of x y naught less than or equal to e of x naught y naught less than or equal to e of x naught y is equivalent to e of zeta I y naught less than or equal to e of x naught y naught less than or equal to e of x naught eta j, where zeta I where I equal to 1 to m and eta j where j equal to 1 to n are the pure strategies. That is, the theorem states that a condition, first condition is that e of x y naught less than or equal to e of x naught y naught less than or equal to e of x naught y is equivalent to another condition, that is e of zeta I y naught less than or equal to e of x naught y naught less than or equal to e of x naught eta j, where the zeta I and eta j are the pure strategies. So now let us look at the proof. So to prove the equivalence of two condition, we have to prove that E of zeta I y naught less than or equal to E of x naught y naught less than or equal to E of x naught eta j. That is, we read it as first condition. It is a necessary and sufficient condition for existence of second condition, that is E of x y naught less than or equal to E of x naught y naught less than or equal to E of x naught y. That the condition is necessary is obvious for first condition hold for all x belongs to Sm and y belongs to Sn and zeta I and are in Sm and Sn respectively. Now to prove that condition 2 is sufficient for condition 1, we notice that E of I1 y equal to summation j equal to 1 to n aij yj. Because the ith component of zeta I is unity and all other components are 0. Similarly, E of x eta j equal to summation j equal to 1 to n xi aij. Hence summation I equal to 1 to m E of xi y xi equal to E of xy and summation j equal to 1 to n E of x eta j into yj equal to E of xy. Now let equation 2 be true. Okay, that is, let E of zeta I y naught less than or equal to E of x naught y naught less than or equal to E of x naught eta j into yj. Okay, which implies that summation I equal to 1 to m E of zeta I y naught less than or equal to summation I equal to 1 to m E of x naught y naught into xi and summation j equal to 1 to n E of x naught y naught yj into yj is less than or equal to summation j equal to 1 to n E of x naught eta j into yj, which implies that E of x y naught less than or equal to E of x naught y naught, which is less than or equal to E of x naught y. Since summation I equal to 1 to m xi equal to summation j equal to 1 to n yj equal to 1. Hence we proved. Next theorem, E of zeta I y naught less than or equal to E of x naught y naught less than or equal to E of x naught eta j reduces to strict equality for at least one I and one j. That is, maximum over I E of zeta I y naught equal to E of x naught y naught, which is equal to minimum over j E of x naught eta j. Okay, so now let us look at the proof. If possible, let E of x naught y naught less than minimum of E of x naught eta j. That is, we take as E of x naught y naught is less than minimum E of x naught eta j. Then E of x naught y naught less than E of x naught eta j for all j, which implies E of x naught y naught into yj naught less than E of x naught mj into yj naught for all j, where yj naught is a component of y naught, which implies summation j equal to 1 to n E of x naught y naught into yj naught less than summation j equal to 1 to n E of x naught eta j into yj naught, which implies E of x naught y naught is less than E of x naught y naught, but which is absurd. Since we get that E of x naught y naught less than E of x naught y naught, which is not possible. Hence E of x naught y naught equal to minimum over j E of x naught eta j. Similarly, we can prove that E of x naught y naught equal to maximum over I E of zeta I y naught.